So today is the last lecture on Scratch. Ooh, we made it far. So after this, our programming lectures are going to be about Python. I'm going to teach you Python after this. So let's go to Scratch one last time, in class at least. Scratch.mit.edu. Oh man, so nostalgic. Okay. So yeah, today is just about writing big programs, how to break down our ideas into little bite-sized pieces so that we can make a program that will eventually do what we ask it to do. It's easier for us as humans to think about problems in that kind of way. Like you look at the big picture, then you break it down into little chunks, and then you work on the chunks. And if the chunks are too big, you break those down. And eventually it'll get down to a reasonable enough size that you can handle the problem. And it all makes sense and it all comes together and it works out. Okay? So yeah, that's essentially the program creation process. Let's talk about that. If I give you a problem to do, or your boss gives you a problem to do, you need to perform some task, right? This is essentially, if it's a programming problem, maybe this works in real life too, this is how you can go about solving it. So first you need to understand the problem, right? You need to understand the problem itself. So that's like, what's involved? Do I need to do math stuff? Do I need to go talk to humans? I don't know. What are the concepts involved? Do I need to move sprites around on the screen, or do I need to like process credit cards? That involves different languages, most likely. Okay? And then, once you understand the problem, you need to break it down into input-output relations. So usually the user is doing stuff. They're clicking, they're giving you numbers. You need to enumerate all of those things so that you understand what you're getting, right? What you have to act on, what the user will give you, what the user will give you. Or maybe let's formulate it as a question. What will the user give you? And then outputs. So based on those things that the user gives you, what are you supposed to produce? Do you have to calculate some number? Do you have to move a sprite around in a certain way? You got to bounce off a paddle, something like that. So what is the answer that your program needs to provide? What is the answer? And I'll put that in quotes because like a game you don't think of it as an answer, but it really is. Like it's a response to inputs, isn't it? What is the answer that your program gives back? Okay, so those are the questions. So your job then, once you understand these things, is to come up with your strategy that maps the inputs to the outputs. So you give me these numbers, I give you this final answer, something like that. The strategy that takes your inputs, computes the outputs. Okay? So it's always going from here to here in this direction. Okay? And the fancy term for that, of course, is an algorithm, a recipe to come up with the final result. Okay? So that's a lot of maybe philosophy, but that's one way to think about a program. You don't really understand what to do until you've broken it down in this way, at least in your mind, right? Maybe you haven't thought that you did this, but you really did. Otherwise, how do you know what to do in the first place? This is just me spelling it out. Are we good with that? All right. So for my first example, let's do number stuff. All right. Let's get a number from the user, and we'll call that n, and then we're going to calculate n factorial. Do we remember factorials from math? So this is 5 factorial. It's 5 exclamation point, right? That's 5 times 4 times 3 times 2 times 1. Yeah. So let's compute that. Let's get the number 5 from the user and give them back 5 factorial. Or let's get the number 100 from the user and give them back 100 factorial. And so this answer is 20 times 6, so 120. And so we're going to compute that, right? So let's do it in the way that I'm trying to teach. The problem is, all right, we have to calculate the factorial of a number. All right, what's our input? Our input is a single number. The user gives us that n. that value that we need to calculate the factorial of. And then the output is also a number, right? It's the factorial of the input. Okay, pretty simple. But now we've broken it down in that way. Now we can attack the problem. All right, so the problem itself is take a number, find the factorial of it. We get the input number, we output the factorial. All right. So once you look at this problem, you might think about cases, and that might make smaller problems for you to then go and solve. So a sub-problem for factorials is, what if the user asks for the factorial of -5? That doesn't exist. Factorials only work for positive numbers, right? Or at least non-negative numbers. So what are we going to do then? Maybe we can yell at the user, tell them they entered a wrong number. Also, what do we ask? What do we say when the user asks for the factorial of the word hello? Because they might type that in too. Let's yell at them even more in that case, maybe. Let's assume they're going to type a number, and maybe the number is negative. If so, we should yell at them. Otherwise, if they gave us a normal number, then we can actually go and compute the factorial. Okay? And we have to come up with a strategy to go and do that. So here's the strategy. All right? We're going to keep two variables. We're going to keep the n variable, of course, and then we're going to keep an out variable. That's short for output. Now, the out variable will eventually hold our final answer. So n, say the user types 5, we'll put 5 into n. Right? And then we'll start the out variable at 1. And the idea is we're going to accumulate stuff into the out variable. So accumulation, by the way, is just you want to keep track of something and you want to build up an answer slowly but surely over a bunch of steps. If you want to make a product of numbers, you better start your accumulator at 1 so you can multiply into that, right? If you started at 0, you'd just keep getting 0, wouldn't you? So when you're multiplying, you start your accumulator at 1, and that's what we're doing here for factorials. But if you're calculating a big sum or something, you better start your accumulator at 0, because otherwise you'd have the wrong answer at the end if you kept adding things into something other than 0, right? So these are our two variables, and here's my strategy that I came up with. Let's keep doing this. Let's repeatedly multiply n into out, so accumulate the value slowly but surely. Out becomes itself times n, and then we'll decrement n. And eventually n will become 0. Once that happens, there's nothing more to put into out. Okay, so here's the strategy. So we have 5, and out starts at 1. Let's multiply 5 into out. So take whatever it was, it's 1 right now, times 5, make it 5. Okay, so now out holds a piece of the factorial answer, right? We need to then multiply it by 4 and 3 and 2 and 1, then we're done. But that's a good start. And then we'll decrement n, because that gives us the next number to put into out. You see that? That's going to be the repetitive process that we do here. That'll be a loop. So 4 now needs to go into out. We'll multiply that in. 4 times 5 is 20. So now out holds 20. You see how we're doing that? You're taking what was in out, multiplying that value by n, and putting it back in out, a new, bigger number. All right? And then we'll decrement n, because I just put the 4 in out. I don't need to worry about 4 ever again. And now I'll put the 3 in. Multiply 20 by 3. That is 60. Now out holds 60. Decrement n again. Does that make sense? How I'm doing that? Then 2 needs to go into out. We'll put the 2 in. So 60 times 2 is 120. And then I'll decrement n. Technically, I could stop here because 1 doesn't really do much. But let's put 1 into out. Why not? Replace 120 with 120 times 1. So 120 again. And then we'll decrement n one last time, make it 0. You definitely don't want to put 0 into out, right? Because that'll kill everything that we've been working on. So once we notice that n is 0, that'll stop our loop. Stop and output whatever is in out. And look, lo and behold, inside of out, we hold the value 120, which is the factorial of the original value of n, which was 5. Does that process make sense to us? Think we could translate that to Scratch code? Let's give it a try. So we're going to ask the user for a number, enter n, and let's make a variable for n. Let's rename this default variable to n. Why not? And then I'll also make a variable for out. N and out, that's what I'm calling them. I'll check them to display them, because why not? But let's get those values from the user. Let's be like, when the green flag gets clicked, Don't ask what your name is. Let's ask enter n and wait. And then we'll get that value. And the value doesn't go straight into the variable n. It goes into answer, right? So let's take care to take it from answer and just initialize n to whatever that was. Okay, so take the value that the user typed, put it into n. That's what the set n to answer block will do. So that's beautiful. And then repeatedly, I want to do the following, right? I want to repeatedly take n, multiply it into out, boop, boop, and then decrement n a little bit. Okay, that process. And eventually, I want it to stop. Okay, so I think because our stopping condition is something that we want to repeatedly check, I'm not going to have a repeat 10 block. I'm not going to have a forever block. I'm going to have the third option. I'm going to have a repeat until. All right. So I'm going to repeatedly do those things, multiply n into out, decrement n, until n is 0, right? Stop when n is 0. So keep going as long as n is greater than 0. Do our stuff. And once n becomes 0, we're done. So we want to stop. So repeat that process until n is 0. Okay? Because eventually n will get down to such a small number. Until n is 0, we'll do our stuff. Okay? Because that's the stopping condition. We don't want to continue once n is 0, right? But until it is, let's multiply, right? Oops. Let's multiply n into out, and then decrement n. So how do we do that? So let's multiply n into out. So that's going to be set out to be whatever it is right now times n. So I need both of those. And then I need an operator, the multiplication operator. Set out to be whatever it is right now times n. That multiplies n into out, right? And then we want to decrement n. So you could set n to n plus -1 or n minus 1, or you could be like change n by -1. That also works. Boop. And eventually n will get smaller, right? And eventually it will become 0. And stop. Once it's done, once this loop is over, we have the right answer, right? We have the right answer in the out variable. So let's just shout it out. Let's say out for 2 seconds, I don't know. How about that? So I could do this. I could be like, all right, enter n, 5. 0? Oh no. What's going on? Enter n, 5. Out is 0. That makes no sense. Enter n and wait. Well, now n's 5. That's good. I think I went too many times. Repeat until n is equal to 0. Yeah, I think I accidentally did too many decrements. Let's see. I wish I could watch this more slowly. Let's debug our code. Let's see here. Let's wait a second in between iterations. Change n by -1. Oh, I'm sorry. I'm silly. Yeah, I don't need this wait. I understand what I did wrong now. I forgot to initialize out. Right? I said n gets whatever answer was, but I forgot to give out 1. The default value for Scratch variables is 0. See, out never changed because we kept multiplying something into 0. That was my mistake. So out better start at 1. I was saying it, but I forgot to do it. That should fix it. So I've added a wait 1 second block here, and so you can see it build up. Now n0, out is 120, just as we expected. Let's do it for, I don't know, 7, factorial of 7. What's that? Repeatedly builds up these answers. It's apparently 5040. Cool. What about the factorial of 3? We know that one. That's just 6. That better be right. Yay, we get 6. Any questions about this? So don't forget to initialize your variables. But it seems to be computing the answer, right? Will it work for every value right now? What do we think? What if I type -5? What will it do? Let's find out. -5, go. Oh, okay, it's just, multiplying out into n into out, and then decrementing n. So you can see that n is -13, -14, -15. Out's pretty big right now. Will it ever stop? No, of course not. Will n ever get to be 0? We keep decrementing a negative number. Are we ever going to get to 0? Absolutely not. So this was one of those edge cases that we don't want to keep continuing whenever this happens. It's just going to build up a bigger and bigger number. It's a very large number right now. It's oscillating actually between very large and very small numbers because it's multiplying by a negative each time. So let's stop that. That'll just run away forever. We'd like to guard against that, right? So let's output an error message maybe if these are types of negative n value before we ever try. So if, oh no, I don't want it there. That was the worst place to put that. Something like that. There we go. So if the value that we have for n right now, if that is less than 0, right? If that's less than 0, we are not in a good place. If you gave me a negative number, then we're yelling at you. Factorial doesn't work for negative numbers! Exclamation point. Something like that. And then, if I didn't do something, this if statement or this if block would allow it to continue, right, to the loop that would go on forever. I can't let that happen. I need to stop the program. Stop the program if we ever got in there, right? Factorial doesn't work for negative numbers, stop. -5. Then we're yelling at the user, no more. +5 still works though. Much better. You always want to try your edge cases too. The factorial of 1, does that work? That's only going to go through the loop once, right? Does that work? Yes, it does. What about the factorial of 0? Technically, I'm not checking for if it's equal to 0. What would that give back? That gives back 1. And actually, the factorial of 0 is defined to be 1, so that's perfect. So yeah, that looks like a good program to me. Ask the user for some stuff, and then calculate a factorial if it's a number that has a factorial that we can calculate. Okay? Any questions about that? All right, saved. Let's do another one. I'll zoom back in for this second program. All right, here's my next example. Let's take two numbers now. Let's sum the numbers from n1 to n2, where n1 and n2 are user input. Okay, so maybe the user, so first of all, we're getting two numbers, n1 and n2. Our output is going to be the sum of all the numbers between them, right? Sum from n1 to n2, that's our problem. Let's understand the problem. If the user types 2 and then 7, so n1 is 2, n2 is 7, we want to add all the numbers from 2 to 7. 2 plus 3 plus 4 plus 5 plus 6 plus 7. Okay, that's the problem we'd like to solve. So we're going to get those numbers in n1 and n2. And then we have to go about summing them all together. So again, you can break it down into some corner cases and then the actual problem. So first of all, what would happen if the user typed a number, the first number that was bigger, like sum all the numbers from 7 to 2, increasing? Well, that's another time that maybe we should yell at the user, I would say. There's no way to get to there, right? we'll have to think about that. But here's how to solve the main idea of computing all the numbers between n1 and n2, including each of them. We're going to accumulate a sum this time instead of a product. So we better start our accumulator variable at 0. Right? So I'll make an out variable now. This one starts at 0. Out starts at 0 here. Right? And then here's what we'll do. Here's an idea. 2 is the smaller number. Let's use the n1 variable and keep repeatedly putting it into out and increasing it, because then it'll become 3, 4, 5, 6, 7, and then we can keep comparing it to n2, because that's how we'll know when we're done. We'll keep n2 the same always, but we'll change n1, right? So we'll add n1, n2 out while it's less than or equal to n2, and then we'll increment n1. So here's how we'll do it. We'll add the 2 in to out, make it 2. Then we'll make n1 3. 3 is still less than or equal to 7, so we're good. We still have numbers to add in. So now we'll put the 3 into out. That makes it 5, right? We're just adding this time. Make n1 4. That's the next number that needs to be added in. Then add the 4 into out. That makes it 9, right? Make n1 5. That's the next number I need to add. That's still less than or equal to 7. I'm good. Then add the 5 in. That'll make it 14. Make this one 6. Add the 6 in. That becomes, I don't know, 20. I can math. And then we can do 7. We make n1 7. Add that in. Then we have 27 sitting in out. I'll write it up here, I guess. It's the only place I have room still. And then we'll make n1 8. 8, though, is greater than 7. That's not a number that I want to put in my sum. That's how I know when I'm done, when n1 becomes bigger than n2. Okay? So I want to repeat all of this. Repeat until n1 is bigger than n2. That was our stopping condition that we just noticed. That'll actually handle this subproblem. We just won't do anything at all. We'll say that the sum is 0, which is technically correct, because all the numbers between 7 and 2 increasing, there are none. So I can give back a value 0. That's totally fine. Okay? So do we understand the problem, understand the algorithm? Are you ready for me to implement it? Let's do it. So let's clear out all the beautiful work we've been doing, and then I'll make a variable n1, I'll make a variable n2, and I'll make a variable out. And then I will display them all. Yeah, so at the very beginning, we have to do a few things, right? We have to, when the green flag gets clicked, we better get something from the user. We better get 2 things from the user, right? We better ask for n1, enter n1, and wait. And then also enter n2 and wait, because those are the 2 pieces of input. And so it's going to be, once we get them, set n1 to that answer. Then when we ask again, answer will change to whatever they type next. And we'll set n2 to that answer. And then out better start at 0. Okay? Initialize all our variables to what they need to be. And now we can do our process. Repeat all this stuff until n1 is greater than n2. Until n1 is greater than n2. And I'm going to need an operator for that. There we go. And so the process was take n1, put it in out, right? Add n1 into out while we can, and then increment n1. That was all this stuff that I was drawing. So let's do that. Let's take n1, put it into out. So set out to be whatever it is plus n1. And that'll change it. And then I'm going to increment n1 next. Change n1 by 1 because that'll be the next number that I want to add into out if it's still valid. Eventually it'll become invalid and we'll stop this. Okay? Once we're done, once n1 gets bigger than n2, we have an answer, right? We have an answer sitting in our out variable that is the sum of all those numbers between the starting value and the ending value. Okay? That should compute it. So let's try 2 and 7. Let's remember to shout it out, I guess. Let's say out for 2 seconds. Why not? There. So enter N1, 2, enter N2, 7. And there it goes. It made 27, yay. And it just happens so fast because it's, I mean, computers are fast. We can slow it down if we'd like. We can wait a second every time we're inside this loop. Try it again. 2 and 7. And there it's going. You can see these values changing up in the top left there. There it goes. N1 is now bigger than N2, and we shout out the answer. Let's try like 1 and 10. What's the sum of all the numbers between 1 and 10? You can see out changing and N1 changing. Eventually N1 will be 11. That's too big. Now we're done. 55. Okay? So that's our program to sum all the numbers between N1 and N2. And it'll also work if we say 7 first and then 2 second. The answer is 0. There are no numbers in that order between 7 and 2 increasing. Okay? What do we think about this program? Does it make sense? Add all the numbers between 2 values given from the user. All right, so I'll save this one. Good. Because the next thing that I want to do for you is show you a very cool trick to make things easier on yourself as you're writing larger programs. We have all these nice blocks, right? These repeat, these set blocks, these ask blocks. Some are even really complicated, like if on edge bounce blocks, right? They do very cool things that would be hard for us to do. But our programs are getting very large right now. Wouldn't it be nice if I could take all of the summing stuff, right, and just shrink it down to its own little block? And then I could use that little block up here and not have to ever worry about writing correct sum code every time I need the sum of something. I'll just write it once and then use it everywhere. I'd like to make my own blocks, all right? Instead of sum n1 to n2, let's do a sum from 1 to n block. So we'll make a block that looks like this. It'll give back, it'll print out the value. It'll compute and print out the value. That is the sum from 1, 2, and then whatever the user wants to put here. We can take input. That'll be cool. And this will just compute the answer for whatever we give it. That'll be really nice. Okay? So we've made a block that encompasses what it means to sum from 1 to a certain value. Okay? And this is all about breaking down problems. That's kind of the goal of the programming part of this class. Goal is break down problems into smaller pieces. And in Scratch, pieces means blocks. Okay, so let's make our own block, our own sum from 1 to something block. Let me show you that. Let's see here, how do I want to do this? Sum from 1 to n block. Let's do it like this. This last piece that we haven't touched yet in Scratch at the very bottom below variables is called my blocks. Let's click it now. Make a block. I would like to make a sum from 1 to block. And then I need an input because I want to sum from 1 to something, anything. There it is. There it goes. And I'll call it n. Isn't that beautiful? This is my block now. It takes one piece of input. It's called sum from 1 to. Hit OK. Now I have this block. And then it also made this. Define sum from 1 to n. Interesting. So let's pretend I have the block. Here it is. Let's use it. When the green flag gets clicked, ask the user for a number. Enter a number and wait. And let's sum from 1 to that number. We'll shout out the answer. That's a very simple program, right? If we had that block. Now let me show you how this works. To make a block like this, we have to say what happens when this block gets run. So the second the program touches this block, it's going to jump up to the definition. Here's the definition of the block, okay? So let me add that as a comment. Whenever Scratch sees our custom block, it goes to execute it, it jumps up to the definition of the block and replaces the input and replaces the n in the definition with our input. Let's say it sets n in the definition to our input. Because I could say sum from 1 to answer, I could say sum from 1 to 10, sum from 1 to 50. I could have a million uses of this block, right? Each time I want them to do a different thing, sum from 1 to this number, sum from 1 to this number. That number is variable. So every time it sees this block, it's going to jump up to the definition of the block, and this piece of input is going to be essentially a variable for us called n. You see that? We can use that inside of the definition. That's going to always be set to whatever we're currently trying to run the block on. So if we're saying sum from 1 to answer, this n is going to be answer. All right? If we say sum from 1 to 10, we're going to jump up to the definition, and then this n is going to be set to 10. It's a variable for us. It's whatever we were given. Does that idea make sense? That's a little confusing once you first hear it, I know. But whenever we start this block, we're going to jump up to its definition. We gave a variable to its input, and that variable is going to be set to whatever was passed along. Okay? Here it's answer, here it's 1, here it's 10, here it's 50. Maybe this will make more sense when I do it. So how do you define this block? How do you sum the numbers from 1 to n? Well, you know how to do that. That's just, well, I don't know. How do I want to do this? Let's make a counter variable. Starts at 1 or something. And then we'll make a sum variable that starts at 0. We'll repeatedly add into sum. So, I don't know. Let's set counter to n. I'm not allowed to change this variable n, unfortunately, so I'm going to have to use a separate variable. I'll call it counter. And then I'll set, let's see here. I'll set sum to 0. And then I'll repeatedly add counter into sum and decrement until I get to 1. That'll be my process. So let me just do that quickly. That was essentially exactly what we just did. It's just one less number to add, right? Instead of n1 to n2, it's just 1 to n. So repeat until counter is 0. This is not the best implementation. You can make this better because it's not going to work for negatives. You should fix it at all the corner cases. Repeat until counter is 0. Let's repeatedly add counter into sum and then decrement counter. So set sum to be sum plus counter. And then decrement counter. And that should, in theory, be everything that we need to do to compute the sum, and then we'll just shout it out once we've computed it. We'll just say the value of sum for 2 seconds. That should be the sum. Let's see if that works. The sum from 1 to 10, it's going to go up and run it. It shouts out 55. That is the answer, right? So I click this, it runs all that code, and it shouts out 55. It jumps up here, and then n gets set to 10, because that was what I gave for that use of the block. So I set counter to 10, sum to 0, and then it all just starts unfolding in the way that we know how to do. Does that make sense? We made a block to do something for us, and every time Scratch sees the block, it needs to know what to do, and here's where we give what to do. And I can use it in a million different places. Sum from 1 to answer, 1 to 10, 1 to 50. It's always going to jump up there with the correct value for n. Enter a number, I don't know, 5. That's 15. And then it'll do for 10, that's 55. And then it'll do 1 to 50. It's apparently 1275. Cool. Very fast. Are there any questions about that? That's a custom block. You can give input, jumps up here with that input and starts executing. That's pretty neat. Okay, are we good with that one? Let me save it. And now let me load, gosh, which one was it? Which lecture did we do Pong in? That was lecture 8. I want to load our Pong program again. Load. I assume it's the largest one here, right? Or honestly, it might not be. I have no clue. Let's see if it's this one. Cool, that was our Pong program. So here's our Pong program again. And notice how we had this lovely if on edge bounce block. And then we had to do extra stuff for the paddle. Let's make a if touching paddle bounce block. Won't that be nice? That'll make it a lot easier to think about. So that'll just be its own little block. We just put it there and it'll run the code that we care about running. That'll make it a lot cleaner in our implementation, I think. Okay? And now we're going to eventually, we're also going to bounce properly. So let's bring this out. Let's make a if touching paddle bounce. We don't actually need an input, sorry. If touching paddle bounce. Block. Boop. And here's its definition up here. And it was this code right here that did the if touching paddle bounce, right? If touching paddle point in direction plus 180. Well, let's just bring that up here. Boop. That's what it means to if touching paddle bounce. And then we'll do this. Look at how clean that is. Isn't that beautiful? If on edge bounce, if touching paddle bounce. One of the two, maybe. Then we'll bounce off. And every time we run this block, it's going to jump up here and do this corresponding code. If we're touching the paddle, then change the direction of the ball, because this is the ball's program right now, and it should bounce off. So that's pretty nice, I would say. Boop. And then also, I promised you this. Let's do the correct bouncing. So when the ball comes in this direction, right now we're having it bounce off this way, which is not very physically accurate, right? It should be bouncing off this way. Does that make sense? So let's do that. Let's see what needs to happen. So it's not going to be a 180. We're not going to flip a 180. We're going to have to do something slightly different. So let's use some math. So if the ball is coming in like this at, I don't know, negative 130, then it needs to bounce off this way. It's got to go that way, right? It's got to bounce off positive. Oh, maybe 130? Okay, if it's coming in straight on, negative 90, it's got to bounce off positive, positive 90. If it's coming in upwards, if it's negative 60, it better bounce off that way. Positive, okay. How about we just negate our direction? I think the Scratch people did this very nicely for us. If we just take the negative of our direction, that's going to bounce off properly, given how they made their coordinates. With 0 up top like that, that was probably the reason they did that. So point in direction, not direction plus 180, but direction times negative 1. That should do it. That's not a good initial. There we go. Oh yeah, look at that. Now it's bouncing off in the correct way. It's the negative version of our current ball's direction. Okay. If touching paddle bounce. We're repeatedly running that, and it's always bouncing off properly. And of course, we can still lose the game. But I think that makes for a cleaner implementation down here, don't you agree? Any questions about that? Hopefully we can see the utility of doing these custom blocks. All right. What next? For my next trick, if we're good, please yell at me if we're not. I have one last example and then a question for you. I'd like to talk again about state machines, okay? We can make a program that asks the user for numbers 1 digit at a time. It's going to be a weird idea, I know, but we can always figure out whether or not the number that the user's typed was divisible by 5 or not, right? So if the user types the number 5, or the digit 5, that's like the first digit of their number, maybe the user types 51080, right? And we're going to get these a digit at a time. So we just see the 5 first, and we pretend that's all that the user typed. And then we see the 1 next. And then we pretend that the user just typed 51. And then we see a 0. Then we think that they typed 510, 510, right? And so they're typing these things a digit at a time, and that's going to enable us to use a state machine. Because look at this. Is this number divisible by 5? I'm pretty sure. What about this first number? If I just thought it was 5, is that divisible by 5? Sure is. What about 51? 51 is not divisible by 5. Why not? What's the trick to use to know if your number is divisible by 5 or not? Because 510, right? That's divisible by 5. Yeah. Very good. Yeah. So you can just look at the last digit. Is it a 0 or is it a 5? Those are the only options, in decimal at least, that tell us that our number is divisible by 5. If it's 51, we know that there's going to be 1 left over if you try to divide by 5, right? That digit, look for a 0 or a 5, then you know that your current number that you've built up is divisible by 5. And so if the user types these digits one at a time, and we're building up a big number, we just care about the last one, because the last digit is the one that tells us whether or not that full number is divisible by 5 or not, right? So we'll have a two-state machine. We'll be like, all right, we're either in the divisible by 5 state or the not divisible by 5 state. Not divisible by 5, and then divisible by 5. At the very beginning, the user hasn't typed any numbers, so let's start out in the not divisible by 5 state. But then the second, if the user types a digit that is either 0 or 5, like this first one, we'll go to the divisible by 5 state, because we know the number is now, if it ends in that digit, divisible by 5. And as long as the user types 0s and 5s as their last digit, they can keep on typing a digit at a time, we'll stay in that state because it's still divisible by 5, right? The second they type some number that is not, some digit that's not 0 or 5, it's not divisible by 5, right? If they type 5, it's divisible by 5, but if they type 51 next, right, then we have to go to this state because it's not divisible by 5. All right, and then if we keep getting numbers that are not 0 or 5, we stay there. Okay, so this is kind of like how we'll have the state machine. We're going to type all these digits in order separately, and eventually we'll get to the end, but we start in the not divisible by 5 state. These are types of 5. That brings us here. The number is now, so far, we think it's 5. It's divisible by 5. Then the user types a 1, so we think it's this number that the user's typed so far. That's not divisible by 5. Then they type a 0, so we think it's 510. We go back to this state, right? Then they type an 8. We go over to this state. Then they type a 0, so we assume the number is this whole darn thing, and we go back to divisible by 5. Okay? Does that make sense? Typing a number a digit at a time, how you could run it through the state machine, and whatever the state that it ends on is telling you whether or not that whole number is divisible by 5 or not, because that was all you needed, was the last digit. Does that make sense? So if the user typed 1, then 2, then 3 to make 123, we just stay over here forever. So we never got a 0 or a 5. That number is automatically not divisible by 5. And none of its prefixes were either. Okay? So let me show you how to program a state machine. The trick is to just use a variable to say what state you're in. State. We have 2 states in this machine, right? not divisible by 5 and divisible by 5. So let's just encode them as 0 and 1. So we're in the not divisible by 5 state if the state variable is set to 0, and we'll be in the divisible by 5 state if the state variable is set to 1. So at the very beginning, it's set to 0, and then once we type our 5, we're going to set our state to 1 so that we know we're in that state now, and use those transitions. Okay? That's all you have to do to implement a state machine. You just got to remember what state you're in, and then remember what transitions you could move, either move out of that state in or to stay in that state in. Okay? Any questions before I implement this in Scratch? So we're going to ask the user to type a number a digit at a time. Repeatedly. Forever, I guess. So when the green flag is clicked, ask the user for a digit. I'm going to repeatedly do this actually, forever. Enter the next digit and wait. We're going to get that digit. And I want to repeatedly do this forever. Build up however big of a number you want to build up, user. I'll take it a digit at a time. My state machine, though, it needs to start in the not divisible by 5 state, which means that the state variable should be set to 0. That's how I'm encoding what state I'm in. So I'll make a state variable, and I'll start it at 0, initial state. All right. And then forever, I'm going to get a digit, and then I want to transition my state machine. So I'm either in state 0 or state 1, and I need to do stuff based on that. Okay? You can definitely simplify what I'm about to do, but I'll just spell it out. So either we're in state 0 or state 1. I need to apply whatever digit we just used and transition based on that. Okay? So if our state is currently 0, where is my state variable? So if state is equal to 0, then, follow the transition using the rules for that particular state. Otherwise, in the else case, we know that our state was 1 and we're over here. Follow those transitions, if possible. Okay? So now we know what state we're in. Now we need to do something based on what value we got. What is our digit if it ends in a 0 or a 5? So if answer was our digit, right? If answer is 0 or if it's 5, then I need to transition, right? Because that was one of the transitions for each of those states. Otherwise, if it wasn't 0 or 5, do something else. That's another if-else. Just kind of comes up naturally. This is going to look complicated. It can definitely be simplified. So if answer was 0 or 1, or sorry, 0 or 5. If answer is 0 or answer is 5. Oops, not duplicate that. Duplicate this whole thing. Yeah. And I need to OR them together. It's going to be a very big condition. If answer is 0 or it's 5, then, oh, come on, I want the whole thing, please. There we go. Then I need to run my state machine. I know that I'm in state 0, right? Because I'm in the body, the if case. And then I know that my digit was 0 or 5, and so I need to transition. I'm here. I saw a 0 or 5. I need to end up here. You see that? That was a lot, I know. So that just means all the transition for us is set our state variable. We need to go to the 1 state. That's our divisible by 5. Okay? Otherwise, if this wasn't true, sorry, I can't really put it all on the same screen unless I zoom out. If this was not true, then we got a non-0 or 5 digit. We're in the else. That means we better stay in our current state. Right? We transition, we stay where we are. you could just hard code it to say, all right, if you want to do something, set state to 0. It already is 0 though, doesn't really matter. That's what we can do. Okay? And then it also is true that otherwise, if state is not 0, then we're in the else case, way down here, right? We must be in state 1, and we better transition based on seeing 0 or 5 or not 0 or 5. It just so happens that the transitions are exactly the same. Oops. So I can do this. And you can get rid of this duplication if you'd like. But this is the fancy state machine. It's like either state is 0 or it's not, or down here. And then either we got a 0 or 5 digit or we didn't. Okay, and that'll change our state. All right? And so every time we change our state, let's just shout out if our current built-up number is either positive, or sorry, if it's divisible by 5 or not. So we'll say divisible by 5 if it is, or not divisible by 5 if it isn't. Just looking a bit weird, I know. So that's that. Let's put these in an if-else. Because either we're going to end up in the state something or something else, right? So our state is changed down here if, oh gosh, Scratch doesn't even like this. It needs to be if-else, by the way. So if our state ended up being 1, then we are divisible by 5. Definitely study this program. It's a long one. If state is 1, then we are divisible by 5. Otherwise, we're not divisible by 5. So I cannot hope to put all this on the same screen for us, but let me try and walk you through it. So enter the next digit. Let's view the state variable as well. Enter the next digit, I don't know, 5. Boop. So it's currently divisible by 5, because what I did was my state is currently 0. I saw a 0 or 5, that's true, so I'm going to set my state to 1. And that is all of this. Then we come down here, state is currently 1, so we say divisible by 5. And now we're back, because we're looping, to ask for the next digit. Oh man, so now we're back up here, type the 1, not divisible by 5 so far, for our current built-up number is 51. Because state is currently 1, so we're down here in this if-else. We just saw a digit that was not 0 or 5, so we go to this else, set state to 0. And that ends the entire outer if-else, as well as the inner one. And state is 0, so we hit this guy, and it says not divisible by 5. Does that make sense? Are you following all that? It's a lot there. You can shrink these into 1, because this if-else and the inner part is the same. So you really don't have to check whether or not your state was something. You can just always transition. But this is me spelling out exactly how to implement this. So we type 51, let's do 0, divisible by 5, 8. We were divisible by 5, so our state was 1, but then I typed in 8, which was not 0 or 5, so we set state to 0. We're down here, this one. And so back in this state. And then if I type one last 0 digit, we were in state equals 0, so we ran this. It was a 0 or a 5, so we set state to 1. It was 1, so we run divisible by 5, and we shout it out. And so forever until the end of time, we can keep on building up a bigger and bigger number, and we're always just looking at the last digit. We're running the state machine. Okay? So that is admittedly complicated, but this can be definitely shrunk. You can also make your own blocks to transition. Okay? But are there any questions about what I did? I made a state machine. I noticed that that would help me solve a problem. I implemented it using essentially a variable to say what state we're in, and then I had a bunch of if-else's, right? Ifs and else's to transition based on the current value of the variable and my current input. That's what it means to move around in a state machine. All right. So definitely try that one out. That was a fun one. For my last slide, I want to give you this again. here's the state machine we just made for divisible by 5, a digit at a time, right? There it is. I would like you to discuss with the people next to you, say hi, take a couple minutes. You don't have to write this down anywhere, but discuss how you might create a divisible by 2 state machine. So you take a number from the user a digit at a time, and then you keep track of whether or not that built up number is divisible by 2 or not. Does that make sense? So try that. Think about how you might do that. Take this as a starting point. It's very similar. Try that for a few minutes, and then I'll talk about your next programming assignment. Bonus points if you go and implement that state machine. You definitely have to do some shrinking. That'd be a very unwieldy program otherwise. A few more seconds. All right, that's my timer. So you can pretty much use this idea again, right? What are the ending digits of numbers that are divisible by 2? Yeah, 0 is one of them. What about others? Like, is 12 divisible by 2? Yeah. 0, 2. Are there more? Yeah, 0, 2, 4, 6, 8. Any number ending in these digits is automatically divisible by 2, right? And so you can just change things around, saying like, all right, these are the digits that make it divisible by 5. Just swap those out with the ones that make it divisible by 2. And you'll transition to the, hey, that number that you've built up so far is in fact divisible by 2 state. Otherwise, if you see a 1, 3, 5, or a 7, or a 9, right, then you transition away from that, because a number ending in these digits is not divisible by 2. It's automatically odd, right? It's odd versus even, essentially. So that will be your state machine. And so as you build it up, you type, maybe your full number is 1, 2, 3, 4. You first type the 1, that makes you in the odd state. Then the 2 puts you into the even state. Then the 3 puts you back into the odd state because it's 123 so far, right? And then finally you type the 4, and it brings you back into the good divisible by 2 even state. Okay? Any questions about that? Does it make sense how you might do that? All right, so I have two things to talk about now. I can't remember if I saved this. Let me just save it again for fun. I think I already did. Cool. In that case, I'll delete that if I remember. First thing, next programming assignment. Programming assignment 4. I'll give you a while to do this one. We do week 9. This will be the last Scratch program you write, so I want to give you something fun to do. You can write any program you want, in fact. So if you have something that you wanted to do, like based on stuff that you have done, make your own fancy game, go for it. So yeah, be creative for this assignment. Here are your hard requirements. So come up with a program that has 3 key press events. So like you can move up left and right or something, or space key to jump if you want to do all that again. Or you can have a mouse click count as a key press, right? Technically that's a key. Also, your program must use at least 2 if-then-else or if-then blocks, so conditionals. You better use 2 of those blocks, right? Things that do stuff like check if the ball is touching the paddle. Those kind of condition checking. I want to make sure you're good with those. And then also you must use at least 2 looping blocks, so like repeat until, forever, stuff like that. I want to know that you understand looping. Okay, so yeah, those are the requirements. The final requirement should be pretty obvious. You can't exactly copy stuff that we did in class or things that you've already done in an assignment, but of course you can build off of them, make it fancier, do different things, but with the same flavor. Totally fine. So yeah, that'll be your Scratch program if you'd like to do it. Any questions about that one? Whatever you feel like implement it, as long as it fulfills these requirements. You got plenty of time to do it as well. All right. This should be a longer video submission because I have no clue what you're doing, right? You got to tell me exactly what you're thinking. Explain things to me because this was very open. It's all up in the air right now. Okay. So that is Scratch program. If you have programmed before, here is your final assignment for Racket. Read those chapters, do these exercises, and record your video. And if I've given you a custom assignment, just keep doing that custom assignment. Okay, so that will be programming assignment 4. Are we good with that? Do week 9. So we're in week 6 right now. So that'll be 3 weeks. Plenty of time. And then also, you have a test coming up soon. So I promised to give a single midterm in this class. I will do that on week 8. Okay, so we're in week 6 right now. It'll be week 8 when we have the exam. And so I've made a little midterm module down here that I will now release. Not the midterm, though. I need to make the question still. But I'll release this midterm info page, and let's talk about it. Okay, so we are in week 6 right now. And so the midterm will be week 8, as late as it can possibly be. So we'll make it the Wednesday of week 8. That'll be the 28th. Okay, so you show up to class on the 28th. We're just going to be taking the midterm. All right? And yeah, the topic's very easy to say. It's just going to cover everything we've been talking about up to and potentially including week 7. If I talk about week 7 topics, it'll be not a whole lot. I wouldn't try and ruin your day with talking about things that we just went over. But up to and including week 7, so study all the things that we've learned. And most of the points will be towards an essay question because I've been asking you to write a lot of essays. So be ready to type a short little essay into Canvas. This will be all done on Canvas. You'll log in on Canvas and take the midterm in the class. Okay? And yeah, here is the format. It will have some multiple choice questions, some short answer questions, a mix of those, and then also your essay question that's worth the most points. All right? So the short essay is going to be on topics relevant to what we've talked about, and then the short answer / multiple choice problems that I'll make will be on the topics from this cheat sheet that I have so nicely made for you. Okay? So here is your cheat sheet. You can pull it up as you're taking the test, but it has the logical operators on it that we learned, some important ones, as well as the logic gates for the circuits that we've learned. Okay, those are the 2 pages of the cheat sheet, so wink, wink, look at that. Okay, that will be the topics of those kinds of questions. Also, the test, it'll just be open book and open notes, so feel free to bring whatever you want. The only thing you can't do is talk to a human that's not me. You can ask me about the questions. You can't just like go on Discord and ask your friends about the questions. I think that seems fair, right? So yeah, that'll be the midterm. It'll be on the 28th. That's the Wednesday of week 8. Okay, any questions about that? So yeah, this is a nice enough class. We only have to have one midterm. For my other computer science classes that are major classes, we have to have 2 midterms. So I'm very excited about the 1 midterm for this class. Much less work. All right, so yeah, I think that's everything that I wanted to say. Anything else about anything that we've talked about that you'd like to ask? Are you happy? All right, that's all I've got then.